All right. So there's a few news links you might want to look at. I mentioned earlier, last week, Coinbase issued a blog post from the CEO saying that he doesn't want any more politics at work. And it was not clear what politics he was worried about, but he was going back to the old model where the business of business is business. You should leave your politics at home, and we aren't going to try to deal with any controversial political issues at work. We're going to and anyway, that is very out of fashion these days. Most people want socially responsible businesses. They want them to take stances on controversial issues and try to improve the world. And so 5% of the entire company has quit. We offered them a good package if they want to quit, an exit package, and a lot of them are taking it. So this is an interesting issue. I mean, he's really doing something that would have been very common 10 or 20 years ago in business, but it's no longer common, and it's an interesting case to see how much people expect businesses to be socially responsible these days. I would think in San Francisco, he's probably going to have a hard time with this. In other parts of the country, it might be more the employees that are willing to put up with it. Anyway, so this is pretty unbelievable. The FBI caught this gang of 13 people that wanted to kidnap the governor of Michigan to punish her for passing rules like a lockdown and a mask ordinance for the deal with coronavirus, which was so unpopular there that Trump said they should liberate Michigan in a tweet, and a lot of angry vigilantes and armed people invaded the seat of power and such. And this is the gang. We can expect a whole lot more of these. These are the people that they keep asking Trump to tell them to stop doing it, and he won't. So he's clearly going to lose the election, and then his angry fans are going to show up at the election polls to try to intimidate people, and we can expect a lot more of this stuff. There was a real disturbing article I saw a few days ago from sociologists that showed that in the last few years, the percentage of Americans that think it would be appropriate for their side to use violence if the other side wins, has gone from like 8% up to 30% in America. So I don't know how many of them are really going to get guns out there and shoot people, but there are clearly some. And so I mailed my ballot in early. You might want to do that and not try going to a polling place on election day. But anyway, we'll see. But of course, if you don't vote out of fear, then you'll end up with these guys ruling. So it's we're in a really bad place here as a country. Haven't been in a bad place like this since the 60s or the Civil War. So Trump took no precautions to prevent the coronavirus. He didn't let anybody wear a mask. He finally caught it. Then he came out a few days later. He declares himself cured. He says he got a miraculous cure from God. He says he's going to give it to everybody free. And then he said, you don't even need anything. Just ignore it. It'll be fine, which is pretty outrageous. And anyway, so I'm surprised that journalists are still going into the White House. There's now, I think, 36 people that are known to be infected in the White House, and several people have leaked out information that they've been told to conceal the fact that they're coronavirus positive and go to clinics far away from the White House and not tell anybody so they can keep that number down. So it's apparently a lot more than that are infected in the White House. And anyway, BuzzFeed pulled out their reporter. If I was running a news agency, I would be pulling out my reporters. I mean, it's like walking into a battle zone. This is pretty amazing. I've heard about these deep fakes. And so somebody wanted people to pay attention to the deep fakes. So made a few to get their attention.
America. You blame me for interfering with your democracy, but I don't have to. You are doing it to yourself.
So they're all like that, and it's very interesting, very convincing ones. A deep fake of Putin, a deep fake of Kim Jong-il, and then the last one here is a person who got killed in gun violence, and they apparently found some videos of this teenager, and they made a deep fake of him. He's been dead for 2 years, and they made a deep fake where he comes back and talks about how you should do something about gun violence. So anyway, they said there will be these political deep fakes coming, and I haven't heard of them actually being used for nefarious purposes yet. But they're certainly very good. You totally could make a fake video of a politician saying anything. And the point is, it's done with artificial intelligence to sync up the voice and the image and make it seem just like the right person. And so anyway, another fact, all over the whole world, the Republican Party is the only right-wing party in the world that denies that there's any global warming or that humans should do anything about it or that we should stop pollution. This is a lot of cases in which the United States stands alone as the stupidest nation on earth. I think they're in a relatively small group too of just denying that there isn't a coronavirus and saying we don't have to do anything about it. I don't think very many people are in that position, but that's totally where Trump is. And so here's another representative in Colorado who refused to be tested, and now his staff is getting coronavirus, and they have been told to hide the fact that they have the coronavirus and not even let the people they share an office with know, so they can't do any contact tracing, and people can't detect that they've been infected. This is following Trump's example. Just pretend it's not there, lie about it, and cover it up. That is the Republican policy, and on it goes. So in the United Kingdom, they claim they have clear evidence of collusion between Huawei and the Chinese Communist Party, which is why the Americans have taken pretty strong efforts to ban Huawei equipment being used in America, and the British are going to do it too now, apparently. So we'll see what comes of that. I've heard people say that the American trade war against China is having the effect of making China become totally independent. And, you know, the old plan under Obama and such was to try to cultivate close relationships with China so we would have some influence over them. But now we're going to have a Cold War, so we'll have no influence over them, and we'll see what happens. Anyway, so this one kind of was amazing to me. This guy used the library's credit cards to buy toner, and then he resold the toner on eBay and stole $1.3 million that way before people figured it out, which is pretty extreme. And that's Bloomberg. Yeah, I don't like Bloomberg anyway, but Cisco had to pay $2 billion in a patent lawsuit, but this isn't the big one. The big one is Google against Oracle. And that's made it, I think, to the Supreme Court. It's not over yet, though. So here's one from Andrew Yang and his gang. I mean, it's tweeted by them. It's not done by them. But Andrew Yang is the guy that loves universal basic income. And there's quite a few studies that have shown that if you take people who are homeless and you just give them some money, then the classic model in America has been if you gave them money, they would just blow it on drugs and then they'd come back for more. It wouldn't do any good. And that is not true. And here they did what seemed like the most extreme thing. They just gave them a one-time lump sum transfer of $7,500. And what happens is a year later, most of them have got a house and got a job. You know, they really are homeless because they're broke. And if they had some money, most of them would actually do something sensible with it and get done being homeless. So should Oracle's Java API enjoy copyright protection? Well, I don't know whether they should or not. It's a question for a lawyer, but that's absolutely the point of the lawsuit. Oracle wrote, it was Java. Oracle wrote Java, and Java had a license where some uses of Java were free, and some uses of Java you'd have to license. And then Google built Android on Java, and Oracle's argument is that Google owes Oracle a ton of money for the way they're using Java and Android, and Google's argument is that their use is covered by the free use case, and they are battling it mightily in court. But it'll be a big settlement if Google loses. I don't know enough. 9 billion, yeah, some large number. You know, I don't have much of an opinion about it. It's a matter of the law, and I haven't looked into it. So San Francisco has passed a no-fault eviction ban. There is some way where you can say you're remodeling your house or something and make people leave, and now they banned that. So our local government is actually trying to do something to help people who are in trouble because they've lost their job. I mean, it is kind of incredible. In America, it's been more than 6 months now. We've locked everything down, so many jobs are just gone. Most of those businesses have already shut up forever. So like 30% of people have lost their job. It's gone. They've been forced to stay at home, and they have no money at all because the government didn't pass the coronavirus second stimulus. In the United Kingdom, as soon as they had a coronavirus, they just said, all right, everybody gets like 80% of their normal paycheck for the next 9 months, no matter what, which is what you need to do when you tell everybody to stay at home. But we're just not doing that here. We have a very broken system. We're not taking care of the basic needs of our people, which is a pretty simple measure of failed government. Anyway, so let me get down to the cryptography stuff. So here we are. And today we're in keyed hashing. So I've got the slides. I did modify the slides. There was nothing terribly wrong with them. There was an acronym wrong and a couple other things I fixed. So it's a new version if anybody cares. Anyway, So we're going to talk about message authentication codes. Now, we talked about them before. Message authentication code is like a signature, like a hash that you put on a message, but these are better because you make keyed hashes. And a keyed hash is more than, now a hash value like MD5 is just a fingerprint that goes on a file, and you can calculate it at the other end and see if the file is changed. But a keyed hash includes a secret key, so you know not only that the file is not being changed, but you know the person that signed it is the person that shares the key with you. So you have authenticity as well. And we'll talk about how these things are made. So that's the point. If you use a SHA hash, there's no secret value. And keyed hashing is where you create these MACs, or pseudo-random functions, or related things. So MACs is the main topic here. And so a MAC process gives you not only integrity, which is what hashes give you. Integrity means the file has not been altered. And authenticity means the file is actually from the person who claims to be sending it. For example, email is famously does not have authenticity. And so you can send an email and alter the from address, and people don't have an easy way to know that from address is false. The same thing's true of phone calls with that name of this or number of the sender that appears on the phone. That thing can be spoofed. So the point of this is to have transmissions where you can verify the identity of the sender. You must previously have somehow shared a pre-shared key, which is not discussed here, but that's true of most of these encryption schemes. That has to have happened. But once that's happened, you can now know that the person that created this authenticated message was the holder of the private key. And it's used by quite a few systems like SSH. Now, telephony encrypts packets, but they don't use a MAC. And that means attackers can modify the packets and they will fail authentication, but they don't really know where they're coming from. Anyway, so the point is the simplest thing you want is it shouldn't be possible to forge it, right? If the attacker should not be able to send a message and figure out the tag to put on the message, otherwise it's useless. So that, for example, means you shouldn't be able to sniff the traffic going by on the wire and deduce the key. Obviously, that would be a failure. For example, that was true of WEP. You could just do that, and that's an extremely bad system. So if you pass this test, which is pretty minor, then you're unforgeable anyway. And so a known message attack is where you just passively collect messages as they go by on the wire, like WEP. That's a very weak attack, and if your system was to fall to that, you'd have a really bad system. A more extreme attack is a chosen message attack, where I can actually feed in any message I want, and as many as I want, and it will sign them, and I can see the signed messages and try to pump out the pattern. And that's a chosen message attack, and you'd like to have a MAC algorithm so strong that even a chosen message attack cannot get in. And if you, I don't know, some of you may have taken my class back in the old days when you cracked WEP. You can crack WEP this way, but it takes about half an hour. You have to get millions and millions of packets, but there's another one where you pump in data you carefully select, and then you can crack it in just 5 minutes. So, but you really want a system where you can't do either of these things. Now, by the way, in general, MACs are vulnerable to replay attacks because you have a message and there's a authentication tag. And if I just record it and play it back, it is of course valid. It will, that tag will match that message. So what you can do is you can add in security at a higher level. You can include a serial number in the message that increments, and then the person at the other end will notice if you're getting a duplicate of a previous message or not, if you're getting the next one in order or not. So that would prevent me, for example, from recording authentication traffic from today and playing it again tomorrow to log in as you. Tomorrow, it'll know I should be seeing a different sequence number. But that's not in the that's not in the cryptography. That's something added at a higher layer. That's in the data after it's outside what's the rules of the signature itself. So anyway, to make a pseudo-random function, you can use a secret key to create essentially random stuff from a message, and the key derivation schemes use this. We've talked about it before, password-based key derivation. You take, or password hashing to store it is essentially the same thing. You take a password, you go through some kind of hashing function to create an apparently random stream of bits from the password, but it is not unpredictable random. It is like a hash, so that if you have another copy of the password, you'll get exactly the same answer. That's the game here. So 4G telephony uses them to authenticate a card. TLS uses them, you know, they're fairly commonly used, pseudo-random functions. And so the goal here is that you should have no apparent pattern in the output. It shouldn't have a failure of uniformity like RC4 did. And that's the game. It's all right. So if you have an unkeyed hash like SHA-1 or SHA-2 and you want to make a keyed hash, then you have to somehow include the key with the hash. So one thing you could do is just take the key and then append the message to it and then hash that whole thing. And that might work, but the problem is if you consider it a message authentication attack, if I were to capture one off the wire and then I could add another message at the end by just adding it to this with linked extension, and I could create a valid signed message even without being able to know what this one signed. So that's a weakness. SHA-3 is not vulnerable to this, but SHA-1 and SHA-2 are, as we talked about last time, because SHA-3 uses a different algorithm for the last step just to prevent this. They didn't think of that in SHA-1 and SHA-2, so they are vulnerable to linked extension attacks. So, all right, here's another more subtle one. If you just ram the key up right next to the message and there's no delimiter, then if I have a key of 1, 2, 3, ABC and a message of that, I can't tell that from a key like this and a message like that because I'm just ramming them together. I have no way to actually separate the key from the message. And this is reminiscent of WEP, where they actually used the IV as part of the key. It mixes two things together that really shouldn't be mixed together. So Blake 2 and SHA-3 include a specific key mode like we're going to talk about later to prevent this. Another fix would be to include the keys linked in the hash. Link to the key, then the M, something like that. Using the key in some more clever way than just appending the message to the key is what's needed to prevent these errors. All right, so here's another way. You can just put the key at the end instead of with the message. That'll prevent the linked extension attack, because if you have measured one of these and then you cannot create what you need to create for a longer message is M1, M2K. You can't get there by adding to M1K. You'll create M1K, M2, and that is not the correct tag for the message M1, M2. So just putting the key at the end would be enough to stop these linked extension attacks. But if you had a hash collision, then of course those tags will collide too. And this is true, by the way, of logins. You may remember back in the old days, if you would have a BIOS password on your machine and you didn't know the BIOS password, it would put a little number in the corner. And if you type that number in a translation, it would give you a working BIOS password, because the BIOS passwords were hashed with a really simple algorithm like CRC32 or something. And even if you couldn't remember the BIOS password, you could just calculate a new number that would hash to the same thing. So that's what can happen here. If you find two messages with hash collision, then you can just use the signature from one message in the other message. So there is some degree of forgery there. But of course, that's only if you use a hash function that has known collisions. All right, so anyway, the HMAC construction is considered a lot better. This is the standard in modern systems. And it works like this. It's a little complicated. You have a hash and then a hash again. So you take the key, you XOR it with this thing called the inner pad, and then you add the message and hash that whole thing. Then you append that to the key XORed with the outer pad and then hash it again. And that mixes all this stuff together in a way that there's no way to extend it or to calculate the signature from one message to the signature from another message. And the pads are just a series of bytes as long as the block size. And the key is probably shorter than a block and it's padded with zeros. But this is just a way of mixing the key in a way where it's not just stuck at the beginning or stuck at the end or put in there in any way that's easy to remove. You actually have the key hashed once here and then once again here. So you've really mixed that key in there in a very complicated way that's not easy to reverse. So you can look at it like this. You can specify the function like SHA-256 had this compressed and such. So the key with iPad goes in here, and then you add the message in here, and then you have the outer pad here. So this passes through two stages where this passes through only one, and then you're done with the block and you can move on. So it's that's how it looks. Now there is a generic attack, of course, if you can find a hash collision, which you should not allow. If you're using, for example, SHA-256, then you'll never find hash collision. But if you use something smaller, like SHA-1 or MD5, then you might find a hash collision. And then you'd be able to make certain forgeries. But anyway, the point is you just have to make the length of the signature longer than 128 bits, and then it will not be practical to find hash collision. So I've got some Kahoots about that. This is 7A. Teach. See at 141. And it is October 8th. All right. We got 16 people. All right, I'll wait a little bit longer. Let me set up a place to put the video. All right, maybe 6 is all I'm going to get. I'll give it a few more seconds. All right. Okay, what system lacks a MAC? That's 4G, doesn't have one. Actually, a question, we'll get there later. All right, what's the most successful attack against a MAC? Replay, they're intrinsically vulnerable to replay attacks. There's no defense against that included. There's no randomness. A duplicate message will have a duplicate signature. All right, which hash is not vulnerable to length extension? SHA-3, one of the few advantages of SHA-3. One might be a reason you might want to move from SHA-2 to SHA-3 one day, but so far there's not anything near enough reasons to make anybody do that yet. All right, which system is vulnerable to length extension? Yeah, the secret prefix. If the secret is in the prefix, then it's already included in a hash you might seal off the wire, and you can add more to the end of it. That's the problem. Putting just one secret right at the start makes you vulnerable to length extension. All right, so MSG, you'll have to tell me who they are. Sounds like Chinese food. And ABC is more of the same. And Daryl, however, is a name. So Daryl's going to get his points. These other people, aha, I see a name for one of them, MSG, okay. All right, I got them both, good. All right. All right, save that. All right, now there was a question about one of these slides, so let me go back. Up here, he says, right. Add the message. It's not there. I'm not seeing your question here. Yeah, slide numbers are probably different than the old version you got on the website. Tell me which one. HMAC, this one here? I did fix, there was some extra junk down here that didn't belong there. So this is in fact simpler than the slide on the website. So OPAD and iPad are just a series of identical bytes. And there's the message. The message appears only here. And this is just appending. So you take the key, XOR the iPad, and then you just append the message to it here. And that ends up getting hashed twice. Okay? Yes, that's right. The double pipe is what they use for append. Good, okay, all right. So you can make these things from block ciphers. In fact, hash functions are quite related to ciphers. We talked about this. They just have a series of very similar operations inside there. CMAC uses a block cipher. All right. And so here's CBC MAC, which is incredibly simple. Remember how MAC worked. You'd have an IV, then you encrypt it with a block of text, then you take the output and encrypt the next block of text, and take the output of this and encrypt the next block of text. So the last ciphertext block includes information from every other block. So all you do is throw away everything and keep only the last block. That's a hash. It's a little screwy, but it does kind of make sense. This does depend on every bit of the input. And the IV doesn't matter. You just set it equal to 0. So you could use the cipher block chaining, AES, as a hash function. And that's what this did. All right. It turns out that it has a defect, as you would imagine, and it's the same defect that we saw when we did the padding oracle. The problem is you take the output of one block and include it in the next block, that's fine, but the way you include it is too simple. This simple XOR right here is a very simple operation to perform and a simple operation to reverse. So what this means is if I have two messages with tags, so I have a message 1 and a message 2, and I get a tag 1 and a tag 2, then I can construct the tag for this message, M1 appended to M2 XOR T1, because when you do it, you'll get the same result as T2. So I can now construct a message, a second message with the same tag from these. So I can forge a valid message. Now, I'm not controlling the content of that message, but if, for example, you were to design a system where all I have to do is send you a message with a valid tag and it takes that as authentication, then I could forge a message with a valid tag this way. And that's what you get from combining the blocks in this excessively simple way, where it's just the XOR of one block into the next block. All right. So if you want to fix it, then the same fix is almost always the same. You want the last step to use a different key. And then I won't be able to forge things. So here you use key to create key 1 and key 2 in some way. And then you encrypt the last block with a different key. And for some reason, which was beyond me to really know why, they actually did it with 2 keys. And they had a system where if you don't need to pad anything, you use key 1. And if you do need to pad anything, you use key 2. So it's a little bit of a wrinkle, which is not obvious. But anyway, that was this improved system for CBC MAC. All right. Anyway, so then you got other designs. There's dedicated designs. Now these used hash functions and block ciphers. Hash functions that were designed for a different purpose, to hash a big file and see if it changed, and block ciphers that were also designed for a different purpose, to encrypt stuff, which would then be decrypted. So as you might imagine, those are not really the best way to do it. They work and they're relatively secure, but they're not really the most efficient. So if you actually start over from scratch and design a system just for making Macs, it turns out you can make them a much, much faster. And that's what Poly 1305 is. So what you do is you make this thing called a universal hash function. And the point of this thing is it's not supposed to be as strong as a cryptographic hash function, because we're not going to use it for the same purpose as one of those hash functions like SHA-2. It's going to have a secret key and a message and calculate the universal hash. And the only requirement is that you aren't ever going to get the same hash for 2 different messages for a random key. And so since the way you're going to use this, it's not going to require the usual hash function requirements. So for a simple one, you just make a polynomial expansion. You just take a series of each block, you multiply the key by a higher power, and then make it mod p. So this is just very fast to calculate. And this will give you a universal hash, but you have to use a different key for every message. Because if you were able to put in two different messages with the same key, then I would have two equations here, and I could solve them to gain information about the key. Remember, a lot of these systems we talked about before, you have to have a different nonce for every message. So here you have to have a different key for every message. And so you can build a MAC from these things using two keys, key one and key two, and a nonce. And this turns out to be satisfy the cryptographic requirements for message authentication code and be much faster. So you have a universal hash, a pseudo-random function, and a nonce. And so that's what Poly 1305 AES does. And it turns out it is much faster. It only has to take one object, which is only one block size, and calculate AES just on that. The message is used only here, and it's considered quite secure. So as you'd think, reusing something that wasn't designed for this might work, but it's a waste of your computing resources. So there's another one. Poly 1305 is optimized for long messages, and SIP hash is designed for short messages. So it's another alternative, and it just uses XORs, additions, and word rotations to scramble things around. So, you know, they've figured out what the essential parts of it are and removed the unessential parts. So things that can go wrong. You can have timing attacks, of course. We talked about these before. For example, here, if you're comparing a MAC to decide if it's correct, you send me a message and you send me, say, the supposed signature, and I'm going to calculate the real signature. And then at the last step, I'm going to compare them. So I'll compare the first byte of this signature to the first byte of that signature. And if it's wrong, I know I failed. If I do this, then certain forged signatures will take longer to compute because the first couple bytes are correct. So this is an example of the kind of code that leads to timing attacks. What you should do is compare every byte every time, so you take the same amount of time all the time. And that's what you have to do, write constant time code, which is difficult. But if you don't, then you have timing attacks. All right. And so if, of course, the attacker can get the internal state of a sponge, we talked about this before, the sponge soaks up data from every block and then you squeeze the hash out. And of course, if you can get the internal state, that includes, that's going to give you information about what's coming out. So it's an issue for some of these, but there are some functions that resist that attack better than others. All right. Like the really modern ones like Blake resist that attack, as we talked about last time. So let's take a look at 7B. I'll give it a few more seconds, but I think 6 is the number of players I expect. Aha, good. Anybody else? We'll go with 7. All right, a hash function that is not collision resistant. That's the universal hash function. All right, the fastest system for long messages. That poly system designed for long messages. And which one's for short messages? SIP hash, all right. All right, and which one uses a block cipher, but only once? That's the AES system. Nobody got it, but that's what it is. That's the one that uses only one AES block of calculation. So JP, that looks like initials. I know who ABC is from before. And hash, we'll have to, JP, okay. All right. And who's hash? Okay, good. All right, so I think I know who everybody is. And good. All right, so I'm going to stop this video.